and a little bit of introduction to where we are, how human beings have evolved their telecommunications to the stage that we have got to today. So, and all these changes were really made possible by three main things that happened. One of them was electricity, and also at the same time, the invention of Morse code, and then driven through that, telegraphy. So those three main events happened in the 1800s that made a big jump or made a big push for the next chapter of telecommunications. And by that time, another thing has happened in the world. Most people have taken to ships and started discovering various continents and countries around the world. So because of these two things, population or mankind was spread around the globe, and they wanted to get information from one place to another place that required crossing the sea in one way or another. And of course, at that time, people haven't invented the aeroplane. So any message that needs to be sent from one continent to another continent had to happen through a ship. So a ship would take between 6 to 8 weeks to go from UK to USA and vice versa. So a message would take from one end to the other end, at least to 3 to 6 weeks from one place to another place, depending on the sea conditions, the winds, and so on. So once we have invented electricity and Morse code, there was a significant drive to have some kind of electrical cable to communicate between countries that are separated by sea. So this idea was floated very early in the 1800s, and by 1851, the first submarine cable was initiated, and that was laid between UK and France, which is only about 20-30 kilometers. But that was, again, the two biggest kind of developed nations at that time in terms of technology, was between Europe and UK, and then UK and US. So they were the driving forces behind the first inventions and the first giant steps in terms of telecommunication. So in 1951, a cable was laid between UK and France. And as soon after that, many European countries like Denmark, Norway, Spain, Italy, they were having their own little cables that were laid under the sea to help communicate between those countries. However, even to this date, our benchmark of a cable or any submarine cable is crossing the transatlantic, basically going from UK or Europe to USA. So the first transatlantic cable was designed around 1866. There is a YouTube video. And before we get to this, I will play this particular video in underneath. This was actually the first time we laid a cable between UK and USA.
By the 1840s, a network of telegraph poles connected nearly every American city. And by 1861, a telegraph line reached from New York to San Francisco. But messages between America and Europe still had to be sent the old-fashioned way, on sailing ships that could take weeks to cross the Atlantic Ocean.
And the idea occurred to somebody to build a telegraph line across the Atlantic Ocean.
The transatlantic cable would be the greatest engineering feat of the 19th century, but the idea for it came from an unlikely source. Cyrus Field, a savvy New York businessman looking for something to do.
He knew nothing. He was in the paper business. He knew nothing about telegraphy. But he suddenly had this idea we could put a line across the Atlantic Ocean, which is about 100 times longer than the undersea cable in the world at that time. He was a very determined man. He was not easily discouraged.
Field spent 12 years raising money for the project, crossing the Atlantic more than 30 times to seek investors in England and Europe. He was the right man for what would prove to be a daunting task. First, over 2,000 nautical miles of cable had to be built. The cable consisted of 7 strands of copper wire insulated in plastic, and it weighed over 1 ton per mile. Then, the cable would have to be unspooled yard by yard across the Atlantic Ocean, from Ireland to Newfoundland in Canada. But at the time, there was no ship in the world that could carry the heavy load of insulated copper wire. So 2 Navy ships, one American, one British, would each carry half of the cable. The ships set off together from England on August 5, 1857. But disaster struck 6 days later as the American ship was hit by a wave and the cable snapped. There wasn't enough cable to continue, so the project had to wait another year. For the second attempt, new cable was manufactured, and it was decided that the 2 ships would meet in the middle of the ocean, splice their 2 halves of the cable together, and then go off at opposite directions, laying cable as they went. This time, the cable on the British ship snapped, and the mission had to be abandoned once again. On the third try, both ships reached their destinations on opposite sides of the ocean with the cable intact. On August 16, 1858, Queen Victoria sent a telegram of congratulation to President Buchanan through the line. But a few weeks later, the signal on the cable gave out. Still, Cyrus Field would not give up.
It took them 5 tries. We first had the idea in 1853. It was 1866 before they succeeded.
The Civil War came and went, and Field worked even harder, raising more money for a new, heavier, and better insulated cable. By July of 1865, there was finally one single ship that could carry it, the largest ship in the world, the Great Eastern. But again, 600 miles from Newfoundland, the cable snapped while being repaired. Sailors spent nearly 2 weeks fishing for the cable that had sunk, but finally they had to give up. Still, Cyrus Field knew his new cable would hold out if they tried it one more time. A year later, the Great Eastern successfully laid it across the ocean.
So you can see how many times people attempted to make this journey. And the first cable that was laid in 1850s, it said after the first message was sent from Queen Victoria to President Buchanan, the signal deteriorated. So what happened really was that first message took something like 20 hours to transmit, because they would transmit a symbol and it would get it wrong, and they might have to transmit it several times until it was correctly decoded in the far end. So in order to improve this, the engineers thought the best way to improve the signal is by increasing the power of the signal, because this is how radio signals work, right? If you want to send a signal further, you put more, you transmit with a higher power in the transmitter. Unfortunately, cables don't work in the same way. So as soon as they increase the electricity, it burned the cable out and completely snapped it. So it completely destroyed the cable by trying to increase the signal power in this first submarine transatlantic cable. But after that, after these failed attempts, many tries later, so they managed to eventually have a cable laid by 1866 with the use of the Great Eastern ship that was built by Isambard Crittenden Brunel. So by 1871, the use of undersea cables have spread from that transatlantic route to between Japan, Russia, China, Europe, Indian Ocean. So many countries were slowly getting connected using undersea cables. And the first cable that actually carried a real live telephone call was made in 1891. Because remember, telephones were only invented around 1876 by Alexander Graham Bell. But until then, all they were doing with these cables that were laid under the sea was to send Morse code signals like a telegraph. So it will only be a short message that will send from one end to the other end. So it took a long time, about 15 years since the invention of telephones, to be able to carry a telephone call in on a cable that was laid under the sea. And then it took a very long time for this technology to develop. So it took almost 60 years, and obviously in between those 60 years, there were two world wars that really pushed the telecommunication back to defense rather than, excuse me. Guys, please excuse me. So it took a long time in order to create a cable that had some amplifiers. And as you see, the cable that they laid across the Atlantic Ocean was only a pure piece of copper from one end to the other end. There was no amplification, no signal improvement as it went along. So in 1956, it was the first time they managed to lay a cable with some kind of an amplifier or a regenerator that can take the calls. So the first cable in 1956 was TAT1. It was only able to take 36 telephone calls at the same time. So by another 10 years later, technology has developed so much that we managed to almost increase the telephone calls that can be made simultaneously by about 100. Now, to get a cable from America to Japan, which is the Pacific Ocean, it took almost 1964. So the progress from the first cable to a cable that we actually carried telephone calls and was useful for normal human beings took a long time. It took almost 80, 90 years for that technology to develop. Now, from that point to today, we have millions of cables laid around the world, each carrying millions of telephone calls, millions of data at any given point of time. So that part of our history, the last 50, 60 years, has been a huge, rapid development. And all I can see at this point of time, that speed of development and speed of requiring traffic or data increasing at the same or even much faster rate as we go along. So which means in your future, when you leave the campus and when you go into industry, you will have many job opportunities because, as I said last week, telecommunications have become one of the main necessities of human beings. So what are the main components of a submarine cable system? Submarine cable systems consist of some terminal equipment, which will be the equipment that converts your telephone calls into a series of zeros and ones. And we are talking about fiber optics. So those zeros and ones need to be converted to optical pulses, depending on whether it's a 0 or 1. Then there is a cable that carries that information under the sea, which is a submarine cable. And sometimes these cables not only go to one country, they actually serve several countries. And increasingly, the new cables that are designed today, a single cable will connect probably 20, 30 countries at the same time. In the olden days, when we designed a submarine cable, it went from one point to another point. They were called point-to-point links. They were only predominantly connecting two countries together. So nowadays, we are connecting multiple countries together. In addition to that, we also have amplifiers to amplify the signal under the sea. These cables, depending on where the location that you're going to lay the cable, have different amount of protection around it. And then all this network, including the units under the sea, have to be managed. Somebody has to stay there 24/7 to look after the health and react to any problems at any given time. In addition, we also have cable ships that are stationed around the world. In every main ocean, there is a company who sits there in order to maintain any cable cuts or repairs that are required. Now, you might be surprised that a ship like this today costs nearly $2 million a day just to sit in the sea. So even though you guys don't make a call, you still have to pay for at least 5 or 6 of these ships stationed around the world, costing almost $2 million a day. So these cables that we lay under the sea have different amount of protections. And it depends on how vulnerable or how easily they get damaged. Usually, you might think that cables that are under the sea will get damaged much more easily. But that is not the case. Usually, the cables that get damaged easily are the cables that are laid closer to the shore or closer to the land side, because most of the fishing activity, most of the shipping happens, or their impact happens closer to the shore end rather than in the deep ocean. And most of the rocky outcrops, or most of the rocky seabeds, are also found closer to the lands rather than in the deep sea. Most of the deep sea is usually pretty sandy and pretty soft for a cable to land. And last week I saw in my questions, somebody asked, do we lay the cable along the seabed? Yes, all the cables are laid along the seabeds. They don't hang from one end to the other end, because when you hang a cable, the sea currents will move the cable around. And if you imagine this is a 6,000, 7,000 kilometer cable, there'll be a huge amount of tension on it. So in order to stop that, we actually lay the cable along the seabed. So the deepest part of the ocean that we lay is about 8 kilometers or 8,000 meters. So these cables should be able to survive the pressure of water up to about 8,000 meters. The only significant issues we see under the sea is usually volcanoes, earthquakes, and sometimes you can have rocky ridges. But when you see such activity, we will put some armored cable. So when you are closer to the shore, we will have two circles of steel armoring. So there will be steel strands protecting the fiber which is in the middle. When you are getting slightly towards the deep ocean, we go with a single round of steel armoring. And in the main ocean, the deep ocean, we actually don't use any armoring. We just only use some rubber or plastic protection around it. So a submarine cable is usually made out of few optical fibers. And optical fibers are the size of a hair. These optical fibers, usually on a submarine cable, we only have about 8 pairs. So that means 16 fibers. One fiber will take data from A to B, and the other fiber will take from B to A. So to connect two countries, you always have to have two fibers. One doing transmission on one side, one direction, the other one doing the transmission to the other direction. So always optical fiber comes in pairs or two fibers together. So The optical fibers are then set in a little petroleum jelly. It's like the jelly you make at home, but it's made out of petrol, so they don't freeze up in the cold weather. And that gives a little bit of a cushion for the optical fibers to sit in without getting damaged. Around that, we have a copper tube. And that copper tube acts as provides two activities for the cable. One of them is to protect the fragile fiber that is inside. Secondly, this copper tube carries the electricity that is required to provide to power up the amplifiers that are under the sea. And beyond that, there is a polycarbonate structure and an aluminium water barrier. So this aluminium stops any water getting inside this cable. And then you have your two parts of the steel wire. You have some tape, and then you have a polythene surrounding or a plastic surrounding. So a fiber optic cable is designed to sit underwater for 25 years. That's usually the lifetime of a cable. And it's supposed to stay under the sea at a maximum depth of 8,000 meters. Now, if any of you who have been to a swimming pool and gone down to the deep end, maybe 2 meters, 3 meters in depth, and hold your breath underneath, imagine how much water pressure your lungs and your stomach is feeling. Now that is at a depth of 3 meters. Now imagine 8,000 meters. So even a cable like this, even if it doesn't have life, it still undergo a lot of stress due to the pressure of the water. In addition to the pressure of the water, these pressures causes some of the gases like oxygen, carbon dioxide to become liquidified. And those liquidified gases will also start to attack the chemical compounds that are in this cable. So after some time, although you don't get oxidization because there's oxygen under the sea, but you get oxidization because the oxygen that is dissolved in the water attacking these cables. So even the design of these cables has an incredible amount of engineering. So it doesn't not only take you a telecommunication engineer to design this, it requires mechanical engineers, it requires chemical engineers, it requires a lot of people who know about hydraulics and water depth and such disciplines to come together to create a fiber optic cable that sits under the sea. Usually, as I said, we have up to about 8 pairs. Nowadays, we can get up to about 12 pairs. And each of these fiber has a different color so that in each end, they can identify which color is connecting to which country. These galvanized strands, again, protect the cable from the inner part of the cable from any rocky outputs, any fishing nets, anchors dropped by ships. So they will protect the cable from those activities. If you are close to the seashore, like say in Sri Lanka, the fiber optic cables come into the country around Gold Face Hotel in Colombo and in Mount Lavinia. In both sides of St. Thomas's College, you have few cables coming in. Most of these cables are buried when it's coming into the land. They're usually buried to about 3 meters of depth, so that if a ship or fishing people, they drop their anchor and drag it along the sea floor, these cables are protected. However, with time, some of the sands can shift, some of the cable can move about in the sea, and these can pop out of this the burial, so they can get into trouble after some time. especially if there's a stormy condition or a tsunami that has come to the country. This would result in these cables becoming exposed. So this is a quick video on about how they actually manufacture the cable, the fiber optic cable.
The clear glass fibers initially undergo one of two types of coloring processes: UV inking, which colors it in preparation for ribbonizing, and loose tube processes, or tight buffering, which provides both color and a protective coating. In the UV inking process, a specialized ink is coated onto each optical fiber. One of 12 colors is used to properly identify the optical fiber within the tube or ribbon in accordance with industry standards. After the inking step, the optical fiber quickly passes to a curing enclosure that rapidly cures the ink to form a permanent color coating and then wound onto a take-up reel. The color-coated fiber is now ready to be put into loose tube or made into ribbon fiber. For tight buffer cable products, a colored PVC coating is applied that increases the diameter of the fiber from 250 microns to 900 microns. This process is called tight buffering, which, in addition to providing a color to identify each fiber, allows the resulting cable to be flexible, yet rugged and easily mated to mechanical connectors. For these reasons, the tight buffered cable design is the preferred fiber cable design for indoor cable applications. At this point, fibers destined for loose tube or tight buffered cable proceed to the sheathing or tubing process. Fibers destined for ribbon fiber cables must undergo an additional intermediate step called ribbonizing. Fiber ribbons are created by serving 12, 24, or 36 individual fibers side by side into a coating die that encapsulates the fibers with a UV curable matrix material into a fiber array. In a process similar to the inking process, the ribbon leaves the coating die and passes through an intense ultraviolet light source that cures the matrix and solidifies the ribbon. The completed fiber ribbon is then wound onto a supply reel. Before the ribbon can be used in any cable, however, it must be tested to verify that its structure and dimensions meet specifications. A small length of ribbon is cut from the reel and placed under a microscope. A technician carefully examines the ribbon sample and fully documents the results. Only if the sample passes inspection can the reel go on to be used in a fiber optic cable. All three of the basic fiber cable designs, loose tube, ribbon fiber, and tight buffered cables, require some form of sheathing process. This is usually another intermediate step, but can be the final production step for small premises cable designs. Here we see a sheathing process for OSP fiber cable that begins with a number of reels of color-coded fiber loaded onto a machine that supplies each fiber at a constant rate under computer-controlled tension. The fibers come together and are fed into an extruder head that performs two main functions. First, a flow of moisture-blocking gel surrounds the fibers. Then, molten colored plastic is extruded around the fiber bundle to form a loose tube around the fibers. Immediately upon leaving the extruder, the hot, soft tube is passed through a long water-filled trough that slowly cools and hardens the tube. The completed tube is passed through an optical micrometer to verify its diameter is within specifications. It is then wound on a take-up reel to be used later in the cabling process. As part of our quality control process, we periodically test fiber tubes to verify that there is sufficient slack fiber within the tubes. This additional fiber slack, also called excess fiber length, or EFL, allows the cable to expand and contract around the fibers without causing stress or attenuation problems. To perform this test, a section of a tube is placed on a special test fixture that accurately cuts it to a predetermined length. The tube is opened midway along its length and the fibers are removed. One of the fibers is separated from the bundle and is mounted between a pair of measurement blocks. A micrometer wheel is carefully adjusted to just bring the fiber into tension. A digital readout displays the fiber length, which is then compared to the known length of the tube. In a different sheathing process, we see tight buffered fibers being fed into an extruder head along with special strength yarns. A fire retardant plastic material is extruded to form the protective tube around the fibers. In this case, the tube is also the outside protective jacket for the now completed cable. Ribbon fibers are handled in a similar manner during the sheathing process. 1 to 30 ribbons are oscillated in one direction prior to being fed into an extruder head, which forms the tube. This oscillation allows for a predetermined amount of fiber slack to be maintained within the tube. PFM gel or dry water blocking agents are also inserted prior to the tube being formed around the ribbons. Depending on the number of fibers required, multiple tubes of fibers may be needed to create the desired cable. The process of combining multiple tubes is called stranding. Reels of fiber-filled tubes are loaded on the payoff equipment of the cabling line. In this example, we see the production of a loose tube stranded cable. The process begins with a reel of fiberglass rod that will become the cable's central strength member. Along with the fiberglass rod, a number of reels of colored loose tubes containing fibers are fed through a series of rollers and guides that straighten the tubes and position them in the correct relationship for the next step in the process. The strength member and tubes then pass into a machine that winds the tubes in a reverse oscillating wrap around the central strength member. Here, you can easily see how the wrap periodically reverses. The cable is then covered with a layer of moisture-absorbing tape. This unjacketed cable subassembly can be used later as the inner layer of a multi-layer stranded cable, or be surrounded with steel armor for use in an underground cable, or simply be covered with an outer jacket for general-purpose applications. The final phase of fiber cable production is the jacketing process. The materials used for the outer cable jacket are chosen for the intended application of the fiber cable. For most OSP fiber cables, Superior Essex utilizes medium-density polyethylene due to its durability, moisture resistance, and low coefficient of friction. High or low-density polyethylene can also be used for select OSP cable designs that require different performance characteristics. Polyvinyl chloride, or PVC, is typically used for the jacket material in our premises cable designs. PVC is a thermoplastic with good flame and abrasion resistance, making it suitable for raceways, indoor-outdoor cable structures, ducted environments, and most riser-rated and plenum-rated locations. The jacketing line begins with the reel of partially completed cable we saw manufactured earlier. This cable passes into a machine that spins a series of flexible fiberglass strength members in a web-like configuration around the cable. The web-like design avoids torque problems, which would cause the cable to have a preferential bend. In order to make it easier to access the cable core where the tubes and fibers are located, one or more high-strength ripcords are added. Here, the red ripcord is seen traveling parallel to the cable as it moves toward the jacket extruder. The jacket extruder is simply a scaled-up version of the tube extruders we saw earlier. Molten jacket material is injected at high pressure and formed around the moving cable. When the cable leaves the extruder, it is very hot and quite soft, so it must pass through a long cooling bath while being kept straight to prevent the cable from developing a permanent curl. When the cable exits the cooling bath, it is passed through an optical micrometer to verify that its diameter is within specifications. Cables used in direct buried applications often require corrugated steel armoring to prevent rodent attack as well as damage from sharp rocks. The corrugated steel armor is formed from flat steel tape that is supplied on large reels. The cable, armor, and a ripcord are fed through a forming tool that wraps the armor around the internal cable elements. The newly armored cable now passes through an extruder where the outer jacket is applied to the cable. After jacket extrusion and cooling, the cable passes to the jacket printer. Here, a hot foil printing process transfers white ink into permanently indented print, which includes cable type, fiber count, date of production, footage or meter markings, and other required information. The completed cable is then wound onto large reels for shipment to the customer. However, one critical step still remains. The cable must go through our final test process to ensure that all fibers meet optical specifications established by Superior Essex. A short length of cable is prepared to expose the fibers to be tested. In this example, the technician is testing a ribbon fiber cable. All of the ribbons within the cable are prepared and inserted in test fixtures that are sequentially plugged into an automated test station. In this way, each fiber and every ribbon of the cable is quickly tested and compared against our specifications. Once the cable passes all tests, the cable...
Okay, I'm sorry that video has been pretty long, but you can see the various stages that has taken a few pieces of fiber optic cables, which are the size of your hair, into a cable that is going to sit under the sea for 25 years. One of the things I wanted to highlight was when they were winding the fiber, you could see them spinning the winding structure in one way for a few seconds and then in the reverse direction for a few seconds. So by doing so, they can accommodate any expansions and compressions of the fiber cable due to heat. So some of these fiber will be sitting under the sea, which is normally a constant temperature at about 4 degrees centigrade. But the parts that are sticking out into the beach could go through different temperatures on the different parts of the world and in different times of the year. So if it's for some reason, this is a cable used in the Middle East, during the summer in the Middle East, it could be up to 50 degrees centigrade. Whereas in the winter, in some places like Siberia, Canada, it could be about minus 40 degrees centigrade. So depending on the temperature that the cable is going to suffer, the inside, the fiber optics and the whatever's inside the cable can expand or contract. And this could create tension and break the fiber. So in order to stop that, they actually wind the cable in one direction for a few seconds and in the reverse direction for a few seconds in order to create a structure that it can withstand this expansion and compression. So the first cable systems, first fiber optic cable systems that were designed were regenerative systems. When it meant regenerative, we will first create electrical pulses, convert them to optical pulses, and those pulses, optical pulses, will go down the cable for a certain distance, maybe about 50 kilometers. And what happens is, as soon as, so you will have a really good optical pulse and it will start going down the cable. And what happens when the amplitude of the signal will reduce because of the attenuation, unwanted signals will get added onto the signal, which we call noise. So basically, by the time it reaches the receiver, the signal is pretty weak and is full of unwanted signals added onto it. So what the regenerator do is it converts the signal back from optical to electrical. It runs through some kind of equalization process. It amplifies the signal and tries to get rid of all this unwanted noise. So it will extract the clock, create the original data stream, and then again go through the process of converting that into new optical pulses and send them in another 50 kilometers. So this type of activity is called a 3R regeneration or regenerative process. It is always converting pulses to and from optical to electrical and back to optical domain. So the first subsea optical cable, which was the TAT1, TAT8, which was done in 1988, was a regenerative cable. So it would have these 3R regenerators, 2 fiber optics going in each direction. And this cable first was laid between Belgium and UK in 1986. And then TAT8, which was from 1988, was laid between US and UK and France. And it was able to carry 280 megabits of data at a given point of time. So the whole of late 1980s and early 1990s, we were laying optical cables using these 3R regenerators. But as we went along, we realized that we could transmit data at much faster rates, but even though we could improve the transmitter and the receiver that is on the ends, because we could not change the regenerators that lie under the sea, it was not easy to increase the data rate of the cables. And also this conversion from optical to electrical and back to optical took a lot of energy. So these cables required a lot of electricity to be pumped in from both ends in order for it to work. As I mentioned before, that these regenerators require electricity to run the electronic components that are inside it. Obviously, under the sea, there are no plug points or solar panels or some kind of a method to create electricity. We need to send the current required to run these devices from each end. So what we will do is that copper tube that is around the cable, we use that as a wire to send electricity to these regenerators. So one country will be operating at about, say, 4,000 volts. The other country will be at minus 4,000 volts. That would create electrical current to flow through the cable. And that electrical current will provide the electricity for these regenerators. So by 1986, the research into developing an amplifier that is capable of just amplifying light itself without converting into electricity was taking a big giant leap forward. Erbium doped amplifiers were discovered around about mid-1980s. So in terms of fiber optics, that marks one of the turning points of undersea cables, because that allowed us to stop this regenerative process, but simply amplify the signal. So what they discovered was, if you take a piece of silicon dioxide fiber, I mean, fiber is made out of silica. If you take one of those silica fibers and take a small piece of some little atoms of erbium, and if you put some erbium atoms inside this silica in a school cricket, right? All these people from either Ananda or Nalanda, whichever school you go to watch the match. And after some times, you will meet your friends, have some alcohol, and you get into this quasi-excited state. So alcohol is like the 1480 nanometer light. All these people who went to the thingy, watch the match, are these electrons that are staying in the ground state. Now, by lunchtime, because they have had some few drinks, they are all very excited. And what happens? So a girlfriend of the rival school will walk across your tent or the boys' stand. And what happens? And you guys get excited and you start shouting at her or saying bad things. And she gets very excited. She goes and tells her friends, and this is end up in a some kind of a row. So very similar thing happens inside electrons inside a erbium doped fiber. Once they get 1480 nanometer, the energy from the 1480 nanometer light, they go to this excited state. As soon as 1550 nanometer light, which we send our data information through the energy starts transferring from these high energy electrons towards this light that is passing through. So with that, the energy that is dropped when you're going from a high energy state to a low energy state is emitted as light or photons, and that is collected by this 1550 light to energize itself and amplify itself. So this principle can also be created by using one of these structures. We use a small piece of erbium. We have a permanent laser energizing that erbium. And when light goes through at a 1.55 micron light goes through in one side, it gets amplified and comes out on the other side. Obviously, we need to do some filtering and getting rid of unwanted noise. So we can have a very uniform gain across a wide area of frequencies. I know this is very technical, but what I want you to get at is this new discovery allowed us to stop converting our data from optical to electricity and using electrical amplifiers to amplify it. Now we can use a pure optical amplifier. The signal goes through without being converted into electricity. So this technology was then started to be used in optical fibers. So in order to use this, we created optical repeaters. And in optical repeaters were placed maybe between 40 to 120 kilometers apart. Yeah, and nowadays, these optical repeaters, they look like one of these little torpedoes. They have pressure sensors, they have accelerometers to detect any movement under the sea. They have these special designs allow the cable to be bent in any 360-degree movement. So there is an enormous amount of engineering that goes into creating one of these. So this is the optical fiber cable part coming in from both sides. Usually a repeater, the full length of a repeater is about 5 meters. If I open up that box inside, it has electrical circuit to power the lasers inside it. It has all the optical equipment that is required to house the erbium. It has special mechanisms to keep the water out. It has reinforced structures to protect it from the pressure of 8,000 meters of water. So many parts of engineering goes into creating a repeater. So here's a structure that we go through in creating a repeater. And this picture shows the repeater on one side, and they're connecting an optical fiber to the repeater. Once we have joined it, we have to then apply a plastic coating around it. Once we apply a plastic coating around it, we actually run an X-ray on every single repeater to look if this encoding process has been perfect. Because if in the encoding process, if there are any air bubbles, those air bubbles will get crushed by the pressure of the water. And that means the whole structure would collapse when we put it under the water. So any air bubble, which is, I think, 100 microns or something, or bigger, needs to be eliminated. So we had to cut out the whole plastic sheathing and redo the plastic sheathing until we are happy that there's no air bubbles inside it. The equipment that goes under in each repeater has to be very reliable. So that means it has to have less than 100 fit. A fit is number of failures within 10 to the 9 hours. So that means any repeater can only have a fit rate less than 100. That means, again, incredibly high level of component selection, and superior engineering needs to go through in order to create one. And we also make these repeaters very reliable. So if one of these laser diodes have an accident, if that dies, we still won't need this amplifier to work. So in order to do that, we come up with some kind of redundant structure. If one of them have a fault, the other one can go to double the power and provide the same amplification. So this kind of very important redundancies inbuilt in these repeaters. So here's one, we have two lasers. The laser is split between two amplifiers. So if one of the lasers has a problem, the other laser can go into double the power. Today, now the new amplifiers that are designed, they are designed with multiple lasers. So if one has a problem, then another one can take over. If two of them have problems, the other two can take over. So we are creating a lot of additional electronics are put in just to make sure that this thing will last without any repairs for 25 years. So optical cables with optical amplifiers were first put in real commercial deployments in 1966 in TAT12, TAT13. They were 5 gigabit systems. They had one channel working at 5 gigabits. Then Asia was connected through FEA in 1997. Most of these cables are still in operation. FEA is still in operation. TAT 1213 was retired a few years ago. So these were the first amplified systems. There were several amplified systems that were put in, but most of them have now reached the end of their lifetime, which is between up to 25 years. But most of them were retired a bit early because the technology started failing by like 5 years ago. So the next stage of the journey got another boost in 1990s. And this new change was called wavelength division multiplexing. So which is very similar to frequency domain multiplexing. Now, all of you listen to radio. In your radio, you have many stations, FM radio, right? You from 88 megahertz to 108 megahertz, that is the bandwidth of FM. And if you tune your radio every 150 to 300 kilohertz, you will find a new station. So each new station means a new frequency is being used to send data. Similarly, in fiber optics, we don't use frequencies, we use wavelengths. The same thing can be done. If we can have a wide enough spectrum, so we found out that the fiber optic amplifiers have a very wide spectrum from 1.53 microns to about 1.57 microns. So instead of sending a single channel, one of my own professors proposed in mid-1990s, why don't we use very similar to FM radio? We'll send multiple wavelengths, each one carrying different data for a different customer. So from that point, we started using WDM or wavelength division multiplexing. So in a multiplexer, we will have different customers, each with a different wavelength going through an optical fiber. And on the other side, we can split out the different wavelengths to the original components. And they found out that there is very little mixing or very little information being transferred between each other. So we can easily keep the integrity of the data, even though they go in the same fiber. So this type of WDM cables were first laid in 1999. Sri Lanka was one of those benefactors from CMV3. It was designed to operate 8 channels at 2.5 gigabits. Then there was China, US, again, 8 channels at 2.5 gigabits. Japan, US. So now they started to increase the amount of capacity in one wavelength and the number of wavelengths. So this improvements kept going on. I'm not going to tell you what we're doing today. I'll get to that in a later slide. But this level of increments, by 2010, we were on 96 wavelengths, each working at 20 or 40 gigabits per second. So huge amount of improvement was happening with time. So all these links were point-to-point, would go from one country to another country, one country to another country, except for CMV3. Sri Lanka was getting a little bit of a spur. So this actually was going from Mumbai to Singapore, and we were getting a little branch. So slowly, the idea of creating branches started to happen as well. So rather than supporting one country to another country, they were thinking, why don't we start supporting many countries, so you can have, say, 8 wavelengths. If we are sending 8 wavelengths from England to Singapore, why don't we send 1 wavelength into Sri Lanka, 4 wavelengths into India? Like that, we should be able to drop different wavelengths into different countries. So the idea of branching units started appearing towards between year 2000 onwards. So the original idea was that we can combine 3 countries, and each country will have its own optical fiber. So this is what happens on SIMEV3. And these PFEs are the electrical supply that goes through the copper tube to power the cable. So if you have this kind of a triangular 3 countries, these red triangles are optical amplifiers. So we need to provide electricity to them. Country A to country B, we will have country A providing positive voltage, country B providing negative voltage. And intermediately, we use this branching unit as the ground point. So we have consider that as 0 voltage, and then country C will send electricity from from that country to the branching unit. So in that way, we can power up all these amplifiers and provide electricity to it. So if there is a cable cut, for some instance, then we can change how the electricity is formed, and that cable cut location can become 0 voltage, and one country can increase the voltage, the other country can decrease the voltage, and still provide electricity to the repeaters. Sometimes if the whole cable gets cut, then this becomes a ground, so we have a bit of a problem. In order to stop that, we can send some magic command and make the electrical path go from A to C, so that country A and country C will still have communication between each other. So again, design of branching units also took a lot of engineering. I'm not going to go very detailed into these things, but it's not only about sending optical data from A to B, it's also about making sure we run electricity to power up those units that are providing amplification along the way. Now, the latest branching units we have today, they actually drop parts of the wavelengths in one location and picks up another wavelength and carries on. So here it's only a single fiber connecting all of these countries, but part of the spectrum, part of the wavelengths are dropped, used for communicating between A and C and B, and vice versa. So just like the repeaters, branching units also need to have a fit rate less than 100. The other part of the equation is we need to provide electricity through the copper tube to power up these units. So these are done through special electrical units called power feed equipment. Again, these are redundant. If one of the power generators fails, another one should take over automatically. These can provide up to 15,000 volts in each end. And about 1 ampere of current is sent down the cable. So there are, each repeater takes about 45 volts, each branching unit about 26 volt, and each kilometer of the cable has a 0.7 volt drop. So we have to calculate all this, factor all that in when we are designing a power feed requirement required for these applications. So it is very important that if ever you go into a cable landing station, and I know some of you have been to Matara, these have a big button saying switch off. But if somebody accidentally switch off the PFE, it will damage the cable. So if somebody presses this button by accident, there are large capacitors inside them. It will slowly drop the power. It will not gradually go from 7,500 volts to 0. It will take about half an hour to go from 7,500 to 0 voltage to stop any repeaters getting damaged. And the same way, when you're powering it up, again, you have to take a small, little by little upgrade to stop increment to stop the cable getting damaged. So again, huge amount of power is generated, and the use of that power needs to be carefully managed. And if there is a cable fault, automatically their powers will adjust, and that also will take some time. These cables come into land in some location, and in those locations we keep these PFE equipment. So in Sri Lanka, we have a cable landing station in Brownshill in Mathura. We have the Dialogue cable landing station in Mount Lavinia. We have the CMEV SLT station in Mount Lavinia, and we have another station in the Colombo SLT headquarters. So all of these are cable landing stations. Cable landing stations do two important parts. One of them is to provide the electricity and provide a demarcation point for the submarine cable. Once data comes in from a submarine cable, it needs to be distributed to a terrestrial cable. So fiber optic cable systems that operate inside a country has a slight different operational mechanism to the cable fiber optics that are under the sea. But it is like your main post office, or it is like the harbor. When we get data into a harbor, when we get goods into the Colombo harbor, it comes in containers. But if you order something from Amazon or Alibaba, you don't get if you order a TV from Alibaba, it doesn't come in a container to your house. What comes into your house is a small box. So in the harbor, the container needs to be open, the small boxes need to be taken out, and then they need to be distributed to the right location within the country. Cable landing stations does the same thing for our data. Fiber optic cables that come underneath the sea bring big containers of data. Some of them will be for me, some of them for you, some of them will be for the parliament, some will be for KDU. All this data needs to be then distributed and sent out to the various people that they requested. Very similar activity. So that demarcation needs to happen at a cable landing station. Usually these cable landing stations are situated in areas where there is very little fishing. There's no commercial shipping, so we don't put a cable in Port City. It's very unwise. Or in Trincomalee Harbor. Or somewhere where we have tourists. We don't go and put a cable in Unawatuna or Mirissa or Arugambe, because we have a lot of tourist activities, and these are very dangerous. If this get damaged, it could be very hazardous. Again, in environmental areas, we don't push this. And cable landing stations are usually blend in with the other buildings. You cannot recognize it as a cable landing station, and they have very high security. And in order to protect the people, sometimes the cable comes into a beach manhole, which is in the beach. And from that point, they separate out the optical part and the electrical cable, and they bring it separately to the cable landing station. Usually the distance could be about between few meters to about 5 kilometers. So again, very complex structure. There's an electrical part that provides electricity to the repeaters. There's an optical part which actually carries the data. And then all of these needs to be managed through some kind of a computer network. So anywhere in the world, you can figure out if something is wrong with your cable. So usually these people who protect these cables, they run a 24/7 management system to monitor the integrity of the cable. So in Mathura, there is a team 24/7, 365 days a year. Their job is to make sure that the cable and everything is running smoothly. To mirror them, for CMIMI 5, there's another group in Sicily, in Catania, in Sicily, in Italy. Again, they are working 24/7 to support our team in Sri Lanka. So I come to the last few slides for today. Now I talked about the cable. I talked about the repeaters. I talked about how we provide electricity, how we provide branches, the main technologies that we are using. So how do we actually lay a cable? How do we decide where to put a cable? What process do we undergo? So this next few slides contains a few videos, and hopefully you can bear with them. It shows you how this is done. So first, nowadays, most of the cables are planned like as consortiums. That means not two countries, not private owners. A few countries come together and they sit down around a table and then say each one say, I need to have 10 terabits of data from the UK. Let's say chairman of Sri Lanka Telecom goes in, sits down in this meeting, says, most of my traffic comes from Singapore, India, let's say Dubai and London. So I want this amount of capacity on this cable. So few countries come together, they put all their demands on the table, and then they will combine a technical team who will say, take that information and convert it into what kind of cable, what kind of data requirements they have. And then they will, each of these parties will say, okay, I will allocate X amount of money for this project. So after that, this will go through a tender process. Today in the world, there's only about 6 suppliers who can supply for this. So one of them is Alcatel. TE Subcom is the biggest manufacturer. There's Fujitsu, NEC, and Xterra is a very small participant, and Huawei is another upcoming participant in this field. So they are the only suppliers in the world at this point of time. So first they will do is they will go and ask these companies to plan a route. So before I come to that, I'll run this video so I can get some water as well.
Optical submarine cable systems link continents effectively and efficiently. These systems can withstand water pressure down to 8,000 meters and transmit over distances in excess of 10,000 kilometers. Optical submarine cables, with their huge communications capacity and low latency, have overtaken communication satellites as the transmission system of choice. They now carry 99% of international communication traffic.
Submarine wet plant equipment, such as cable, repeaters, or branching units, are carefully designed to operate in the tough conditions of deep ocean waters and stay there untouched for 25 years.
A single submarine cable can contain up to 8 fiber pairs. When building a submarine cable system to provide ultra-fast, ultra-reliable global capacity, it is essential to offer well-proven designs for the optical fiber cable. In deep water, the cable is coated with minimal protection. In shallow water, the cable is overlaid with armor wires. This important device protects the cable from external aggression, such as seabed exploration and fishing. The cables are coiled into the cable tank of the cable-laying ship.
The desktop study is the first report to visualize the cable system that the customer will own in the near future. Based on the desktop study, we will carry out the route survey.
Cable and repeaters are manufactured based on the cable route survey information. Repeaters are placed every 40 to 100 kilometers in the cable system. It is imperative that these repeaters keep operating smoothly over a long period of time in cold, deep water. The repeaters have their own exclusive loading space on the cable-laying ship. The cable ship will transit to wherever the cable will be deployed, and then she will start her operations. Cable landing involves securing the submarine cables on land and linking them to the land-based facilities in the landing stations. NEC can arrange all the necessary permits to land the cable in each country connected by the system. These arrangements take into account local regulations, labour laws, environmental concerns, and the rights of other stakeholders, such as fishermen. The landed cables are attached to the terminal station equipment installed in the landing stations.
So just like Google Maps, nowadays when you want to go somewhere, Google Maps will show you exactly the road where we have to go. Most of the seabed has also been mapped over the years by various companies, and they own the rights for these maps. So whenever we need to design a cable, when we need to design a route, we have to go to these people and get a map. And from that map, we will do a desktop study and plan the cable route where it should go. But of course, there are countries which have been in this game for a long time, like Singapore, Oman, Egypt. These countries have many cables that come into their countries. So because of that, we have certain rules about crossing other countries. So if you're laying a new cable, you are bound to go on top of an older cable that is currently in operation. So in order to protect the older cables, we have certain rules. So we always have to make sure that no two cables will cross each other more than 3 times. If there is a cable crossing, we need to put additional cable into the seabed so that you can lift out the older cable without breaking the cable that is on the top. Remember, everything is 8 kilometers. These are very heavy. It's not like pulling out a string from underneath. So we cannot simply put a cable on top of an old cable. So every time we cross the cable, the new cable needs to put 3 times the height of the water as extra cabling under there. We also don't cross very close to branching units and repeaters. Again, repeaters are heavy, branching units are heavy. It is not easy to lift them up when we are having a cable repair. So this is like the seabed information we get from this desktop study. It will show us what kind of areas where we will have rocky parts, volcanoes, and especially in the Gulf, in the the Middle Eastern areas, we have oil pipelines that are under the sea. So when we are putting a cable, we have to make special structures to protect the oil pipelines, so the cable doesn't sit on top of the oil pipeline. In addition, I don't know whether I'm allowed to say this or not, but there are parts in the sea which are used for military activities. When you do a survey and try to lay a cable, somebody in the military will come and say, sorry, you can't lay a cable there because we have submarine activities or we have underwater warfare. So there are many parts of the sea that you might find difficult to lay a cable because of various reasons. So once we finally agree, come up with the desktop study and get the permits from the military, the environmental agency, the whoever, the oil industry and so on, we come up with the route. Then after that, we have to send a ship, which we call the route survey. A ship will go and run a sonar, I think 110 meters either side of that planned route. So they will go with the ship along the route that you have planned, and then we'll do a sonar, I think plus or minus 10 meters, to see if there's any issues. If they find an issue, let's say they found a volcano on that path, then they will look for another alternative path. So we have to make allowances to this route. So once we have come up with the desktop study, they'll do the route survey with the sonar. Once that is done, we will have to then redesign the cable, look at the placement of the repeaters, see if we need extra armoring. So if they find any rocky parts, if they find any volcanoes, we'll have to add additional armoring on that. So all this activity needs to go happen, and from the point of coming to an agreement and a consortium table, the final cable being laid and operational can take between 5 to 6 years.
Optical submarine.
So once we have designed all that, we manufacture the full cable in the factory. The full cable is assembled with all the repeaters, and it's mounted on a ship. So how do we get from there into laying the cable? So this full cable, entire cable is loaded into a ship. Maybe sometimes it is loaded into multiple ships, and then it is transported to the location where you have to lay the cable. Most of these cable manufacturers are either in New Jersey in USA, in France, or in Norway. So in various parts of the world, and they have to transport that cable to the location where they have to lay it. We start laying the cable from the middle of the sea to the ends. So let's say we are laying a cable from Sri Lanka to Singapore. They don't connect the Sri Lankan cable landing station on day one. They will start maybe 100 meters in the sea from Sri Lanka and start laying the cable all the way to Singapore. Once that cable is laid only, then you connect the two ends to the land. We call the two ends the shore ends. And then there is an awful lot of sensors that are inside the ship and on the cable to help us position the cable. So there are many YouTube videos on this, but I'm just the cable end. The cable has been sorry, let me take the sound of this. So this is the cable landing station, and the cable has been laid all the way to the in the sea, and now they're pulling it into the landing station. So what they do is they initially run trailer buoys, and this is the beach manhole, and they first run a rope and they pull the rope into the landing station. And then the ship goes on laying the rest of the cable along the sea. So this one is called a sea plow. What it does is it uses air jets and creates a hole. And then at the same time it's creating the hole, it starts to bury the cable. So it can bury it up to 3 meters based on the speed of the jet. This is called a sea plow. These are all operated remotely from the ship. We only bury the cable near the shore end, so up to about 500-meter depth only we bury the cable. After that, we just lay the rest of the cable along the seabed as we go along. And if there is another cable, older cable, they don't actually plow it on top of. They just lay the additional cable and then start burying for the rest of the part. And once we have reached the deep water, we no longer bury the cable, we start letting it just along the seabed. And then again, we have a different kind of a rover. This is between 500 meters to about 1 kilometer in depth. It can inspect the cable and see if it needs additional burial. So that's special, again, another special equipment. Again, in the deep sea, we actually don't bury it, we just leave it underneath. So when the water depth is about 1 kilometer, we just leave the cable hanging on the sea floor, as you can see. If we have this type of rocky outcrops, what we do is we put down extra cable. So we make sure that it is, the cable is resting on the seabed rather than hanging across ridges. So we'll always put extra cable to make sure that the cable is nice, sitting right on the seabed. Okay, so this is the process we go through to lay the cable. And I'm coming to my last slide for today. So hopefully I can give a little bit of time back to you. So the last thing is what happened, how do we get faults? How do we do repairs? So when we provide a cable, when we design a cable, each country is given a repeater and a spare amount of cable to be kept in a storage. Now in Sri Lanka, we used to keep it in Hambantota Fort until we sold it to the Chinese. So now our cable storage area is in Galle. So if something happens to CME5 cable, the repair ship will come to Hambantota. We will have to transport the spare cable to Hambantota port. It will be loaded up onto the ship, and that ship will go and carry out the repair. So what happens with cable repairs is, why do we need a cable repair in the first place? So this is a ship that could have laid anchor close to Colombo and is dragging the anchor below. And it can catch the optical cable, and once it tries to pull the anchor, it could break the cable. These are shipping trawlers. At the moment, we have this problem with the Indian fishermen doing bottom trawling. When they do that, the fishing nets with these kind of hooks can pull up the cable and break the cable as well. So once we've done that, once a cable is broken, we send a special ship. It will try to locate one end of the cable. They will pull up the one end of the cable, and they will tie a buoy to it, these floating things, and leave it on the sea. Because when the cable is broken, there'll be two pieces, right? Both pieces are not going to be in the same place now. So we first locate one end of the cable, we pull it up, we tie a buoy to it, and leave it hanging in the sea. Now the ship will go look for the other part, the other end of the broken cable. Again, the ship will locate that other end of the broken cable, pull it up, and to this end of the cable, so they pull up the cable, they will take it into the adjoining area. They will take the spare cable that they got from the storage facility, and then they will splice a new the spare cable into that unit. So, and for that we have like a little plaster or a temporary joint, which we call a universal joint. Again, these joints needs to be properly isolated. They need to have the strength. They need to survive in water for another 25 or whatever the number of years. So again, they need to be reinforced. They will be made out of titanium. The splicing will be done. And then again, we need to put this plastic coating around it, X-ray the fiber. And then once we are happy with that side, we will reinforce it and put that side of the cable back into the sea. Now, this is the old broken part. The second part here is the spare cable that we had in the warehouse. Now we will go to the location where we pulled out the first part of the cable, and they will park the ship right across to the side, pull up that buoy and connect. Okay, so then they will pull up right next to the buoy door first half of the cable. They will pull it back into this the ship. And they will pull it back into the ship. Again, a new joint is done. A new protection section is added, X-rayed. Then the plastic cap is added. And then now the completed cable is slowly lowered back into the sea. Now this process means we are adding additional cable. Every repair, we have to add at least 3 times the height of the water to the cable. So once the joint is done, it is lowered back into the sea and left it on the seabed. So breaking a cable is a very, very difficult thing for us. So I have been working on upgrading a cable between Malaysia and Egypt, and that cable was broken last week. So now we have a big problem. We have a race against time to have that cable repaired before the World Cup. So there are 2 types of cable breaks. So one of them is called shunt falls. Shunt falls is the outer coating of the cable gets damaged, so the copper tube is exposed to the sea. The fiber optics that are inside the copper tube is not damaged. Usually these happens mainly from shark attacks and also from ship anchors damaging it. And sometimes if the cable moves along the sea due to water currents, it could bruise against sharp edges and cut itself. A cable cut mostly happens from fishing nets. Now, usually cable cuts happen very close to the shorelines, except when there are underwater volcanoes or tsunamis. Now, recently there was a huge underwater volcano near Tonga, which took Tongan internet out completely. And when there was the Fukushima earthquake in Japan, it took the Japanese telecommunication lines out. And that was mainly because of the damage to the cables because of these activities. Very rarely we could have pump failures or cable breaks because of imperfect manufacturing processes. Now, these are very common to Mitsubishi made cables. Recently, most of the Mitsubishi went out of business because of building cables, because the reliability of the units were not as good. As I said, repair ship to sit in ocean costs between $100,000 US to $200,000 US. When the cut happens, it needs to go to the spares depot, pick up the cable, and then go back to where the issue is and repair the cable. Depending on the sea conditions, it could take between 1 to 2 months from the cable breaking and repairing. One of the difficult areas that we have in the world is Yemen. Now, if you look at the Gulf of the Red Sea, On one side, you have Oman, and on the other side, on the bottom of Oman, you have Yemen. And on the other side, we have Sudan, Somalia, and Djibouti. So these are very difficult areas in the world. There are no governments. There are politically volatile areas. But for us as cable engineers, why it is the most difficult part of the world is that opening in the Red Sea is only 1 kilometer in wide. If a cable gets cut, it could drift into Yemen or it could drift into Sudanese waters. These are not friendly countries. It's not easy to get a permit. We cannot send a ship to pick up the cable because they might get under attack. So if a cable breaks in that part of the world, it's incredibly difficult to repair it, not because of conditions in the sea, but conditions politically. So the whole of the cable industry or the submarine cable industry, it is not only driven by technology and the issue, the progression of technology. We also have to deal with geopolitical issues that various countries have between themselves. For instance, if you go into a cable in Iran, that cable crew cannot be from the US or any of the European countries. So there are, again, all this needs to be taken into account, makes it very hard for us to run this industry coherently and easily. So just to finish off, what is the history of cables in Sri Lanka? Obviously, we were first connected to fiber optic world with SIM-EV3. The landing station is in Mount Lavinia. Then we connected to Maldives called the Diragu. It's again in the same station in Mount Lavinia in 2007. We have a cable to Bharat Lanka cable system, which is going to India. This purple cable here, Diragu is the yellow one here. This is a festoon cable. It doesn't have any repeaters, but it's got a special amplification structure. Then we got connected to SIM-EV4 in 2005. That goes into SLT in Colombo. SIM-EV5 came into Sri Lanka in 2017. This is the latest cable. This is the first time Sri Lanka actually powering an optical cable. We are part of the bigger consortium, bigger player of the world. So that's really it for today. And I'm going to leave you with this video on the background on the cable, SIM-EV5 cable being drawn into Sri Lanka. While this is going on, I will look and see if you have made any questions for me. And this video is about 5 minutes long. I'll let it play, probably at lower noise. Let me open the questions up and this video is showing the SIM-EV5 cable being dragged into Sri Lanka. This is the boat bringing wide rope. The guiding rope. The guiding rope is now taken from the land to the ship that is holding the cable. anybody from North area will probably recognize the location. In the north of the beach, there is a statue where the cable actually comes from. The cable is slowly being pulled in, so the first bit of it being pulled in, and now the cable. While this one is playing in the background, I will answer some of the questions. So several questions. How does it affect earthquakes after max? Earthquakes are very bad for cable that can be broken. As I explained, Fukushima, and the recent earthquakes will take off the cables. And if it's an earthquake, it's more than an earthquake, if it's a volcano under the sea, it could be active for months, so it's not really any cable. In right, it's 1.6 cable because that particular volcano is fairly longer time. But there is a lot of work being carried out now to allow these cables to detect earthquakes. One of my topics for next week. This is one of the research areas that I'm working on now. How to protect, how to get ourselves warm about it. So the next one is, why do we need coloring of fiber optics? Now, if you have, let's say, 6 pairs of cables, 7, 8 pairs of fiber, inside optical cable, how do we know which one is connecting to India? And if we are connecting half of them to India, half of them to Dubai, going from Sri Lanka, how do we know which one is connecting to Dubai? Which one is the transmit fiber and which one is the receive fiber? So that's why we color the optical fibers, so not the outside of the optical fibers, with different colors. So you know the blue one starts from Sri Lanka, goes to India, and that is the transmit receive fiber. Receive in India, transmit in Sri Lanka. Maybe the red one is the transmit from India, received in Sri Lanka. So each end knows which color is connecting to where. There's another question about what happens to cables when they're old. Really, this is a big problem. It's just like the satellites when they're old. What do we do with them? Nowadays, what we do is we actually pull the cables out from the sea, which we can. And some of them are being reused. For instance, the TAT12, TAT11 cable that went between UK and USA. I work for a company called Xterra, where we pulled that cable out and then deployed in countries which were not very rich, who couldn't afford a new cable, but this cable was satisfying their needs. So we took out the good repeaters, good amplifiers. We removed all the faulty amplifiers out of the system, and we laid it between the USA and Bermuda and Jamaica, Tortola, Bahamas. So various Dominican Republic, various Caribbean countries which were closer to each other. We laid that old cable, and that is in operation. We given it a new lease of life for another 25 years. But really the old regenerative cables and so on, they were actually pulled out. Nowadays, metals that we use to create these cables are very, very expensive and rare. So it makes sense to pull these cables back up and reuse them. How much information can a cable carry? I will answer that question next week because we have progressed so much on that. How many kilometers of cables are there under the sea? This video will answer that while it plays in the background. Does temperature affect fiber optic communication? Yes, and so does lightning, so does water currents. Anything that has any disturbances will affect optical communication. But usually, because these cables sit under the sea, majority of the cable, at a constant temperature, because under the water, even in the frozen ice, the water underneath is at 4 degrees centigrade. So that part is constant. Where we have a problem is when the cable comes out of the sea into the land. In those locations, you could have temperature variations. Why are many cables between some continents, but no cables between Australia and South America, for instance? That is not true. And sometimes, again, it's a little bit about our relationships. Most of the people in South America are closer to people from Spain and Mexico and Portugal. So there are many cables between Portugal and Spain and South America. Another country that speak Portuguese, so Brazil speak Portuguese, Portugal speaks Portuguese, and Angola speak Portuguese. So there is a new cable between Brazil and Angola. So just like we normally talk to our friends and relatives, the world also has that tendency. So they always try to stick to their friends, and similar speaking worlds try to stick to each other. So there are many cables between US, Japan, Hawaii, and Australia. There's many cables between Australia and Singapore. But also, if we have some land in between, we can get more data going through that. So if you lay a cable from Australia to South Africa or Australia to Argentina, the distance of the cable is so long, it might be more productive to send the information via a shorter crossing to Hawaii, to US, and then back down. What is the advantage of using fiber over satellite? I think I've answered that question last week. Can you please check the previous video? International routes. There are many international routes to protect cables, yes. But then again, a few years back, I think about 10 years ago, somebody went underneath the sea in Egypt and actually cut the cable with a saw. And he actually, there's few people try to do that. Obviously, the first few people died because of electrocution. The third man managed it and cut the cable, and they stole, I think, a couple of kilometers of cable and sold it for copper. So there are problems. There are thieves, metal thieves that are happening everywhere. So this is, we do a lot of protection, but it's, again, as I said, how can you protect a cable near Somalia because of the pirates? How can you protect a cable that is in a very volatile part of the sea? So these are all very, very difficult things to do. Are special robots used for cabling repairing? Yes. Actually, more especially we use a lot of robots for deploying cables. Again, as I said, all engineering fields come together. We are multidisciplined. Somebody with robotic knowledge can have a little bit of communication knowledge and come together to work in a cable repair ship or cable laying company. So just to finish off for today, and I will have my last session next time. Engineering is about bringing lots of fields together. Being a telecom engineer is not just about learning about sending data. It's also about how to bring these various disciplines to one place and create an industry that generates out of that. Knowing about electricity, chemistry are all important. So I leave you with this message, and I hope to see you in the next session, which will be my last on this, when we look into the future of fiber optic cables. Thank you.
So, thank you, Dr. Sumudu, for sharing your knowledge with us today. The event for today is almost over. So, I kindly invite all of you to turn on your cameras so we can capture a moment from today's event. The photo will be taken after my countdown. 3, 2, 1. Thank you, everyone. Before we wrap up, I invite Kevin Pereira, the Secretary of the IEEE Communications Society of KDU, to propose the vote of thanks.
Thank you, Aditya. A very good evening to all of you. On behalf of the IEEE Communications Society of General Sir John Kotelawala Defence University, it is my honor to propose the vote of thanks today. First of all, I thank our speaker of the evening, Mr. Sumudu Edirisinghe, for joining us yet again, despite your busy schedule, to conduct another knowledgeable session on submarine cables. Moreover, my sincere thanks goes out to the Dean of Faculty of Engineering, Captain Retired S.U. Dampage, Professor T.L. Veeravardhana, Head of Departments, Advisors of IEEE KDU, Advisor of IEEE Comsoc KDU, Dr. Sanika Vijayasekara, for mentoring and guiding us throughout. My special appreciation goes out to the team behind the scenes, the Executive Committee, Board of Directors, and team members for your immense contribution. Last but not least, I thank all the participants who joined us today. I hope all of you got a deep insight on today's session. Do stay tuned for session 3, which will be commencing soon. Thank you and have a good night.
Thank you, Kevin. Let me take a moment of your time to kindly remind everyone present to follow us on social media by clicking on the links in the chat box. We are now at the end of the webinar session for today. I'm Aditya Satsarani signing off for today. Thank you and have a good night.